Hello everyone, welcome to Ease in UPSC. My name is Trinath Kumar Pothina, and today we are going to venture into a series of lectures covering your Civil Services Preliminary Examination Paper 2, which is your CSAT. In this first lecture, we will discuss about the concept of H.C.F and L.C.M, and in the lecture following this lecture, we will be doing solved examples on these two topics. So without further ado, let us go into the discussion. So this will be a brief outline about what we'll be discussing in today's lecture. Basically, we'll start with the introduction to the number system. We'll look at the different types of numbers, which is very much essential to understand the different functionalities of numbers. Then we'll go at understanding what is division, what is the dividend, divisor, quotient, and remainder. In fact, your entire concepts of HCF and LCM are dependent upon a firm understanding of these topics. Then we look at the tests of divisibility. We'll see the tests of divisibility for different numbers. We'll see up until the number 18. And then we'll go into the definitions of what is a factor, what is a common factor, what are the prime numbers and composite numbers, and what are co-primes. We'll also look at the properties of prime numbers. And later we'll venture into understanding one of the most important concepts in mathematics. It is called the principle of prime factorization or the fundamental theorem of mathematics. We'll look into that with solved examples, and we'll also, from the standpoint of the fundamental theorem of mathematics, we'll try to understand the concept of prime numbers and composite numbers, and also look at why the numbers 0 and 1, which are the only numbers in the entire number system, that they are not prime or composite. We will look at, from the standpoint of fundamental theorem of mathematics, why 0 and 1 are not prime or composite numbers. Then we look at the concept of HCF. It is also called the highest common factor or the greatest common divisor. Then we look at the concept of LCM. It is called the lowest or the least common multiple. Then we look at the relationship between HCF and LCM. So, what are the different types of numbers? You might have come across a lot of numbers in your daily life. So, what are the different types of numbers that are there in mathematics? We start with the natural numbers. Natural numbers are those numbers that we use for counting, and we start counting things from the number 1. So you might have counted umpteen number of times, and you understand that you will not be counting something with 1.5 or 2.6 or 3.7. They are not natural numbers. You will be counting as 1, 2, 3, 4, and so on. So you will start your counting again. You will not start counting from 0. You will start counting from 1. So all the counting numbers are in essence called the natural numbers. In mathematical terminology, it is denoted by the letter n. And what are whole numbers? Whole numbers are nothing but the counting of natural numbers plus the number 0. If you include 0 to the natural numbers, then we get the whole numbers. Then we come to the concept of integers. What are integers? Integers are those numbers that are positive numbers, negative numbers, or 0, but they are not fractions or decimals. Okay, so all these numbers that are either positive or negative or 0 and not a fraction or decimal, they are integers. And please be advised, friends, 0 is neither positive nor negative. So integers are used to perform various arithmetic operations like addition, subtraction, multiplication, and division. And in mathematical terminology, you denote integer with the letter Z. What are rational numbers? Rational numbers are those numbers that can be represented in the form of P by Q, where the number Q is not equal to 0. Why am I saying Q should not be equal to 0? Because in mathematics, if you divide any number by 0, that is not defined in mathematics. So we will not call anything a rational number, or for that matter any number, if you are dividing a number with 0. So rational numbers are those numbers which can be represented in the form of P by Q, where Q is not equal to 0. It is also a type of real number. We'll look at what real numbers are. So any fractional number, say if you take the example of say 3 by 5, this is a rational number. You take 22 by 7, this is a rational number. You take 10 by 3, this is a rational number. So these are all rational numbers where you can represent uh, the rational number in the form of p by q, where p and q are integers. They can be negative numbers, they can be positive numbers, except for the fact that the denominator should not be a 0, and p and q can be, we'll just write it in the, we'll just clarify that. P and q belongs to the set of integers except for the fact that, okay, let me clarify that. Except that q is not equal to 0. The denominator is not equal to 0. Okay. So you have all these numbers 0 by 1, 0 by 2, 0 by 3, all of them give the value 0, but they are rational numbers. Rational numbers also contain the number 0. However, the numbers 1 by 0, 2 by 0, 3 by 0, they are not rational numbers because they are not defined in mathematics. And one of the important tips is, how do you understand whether a number is a rational number or not? Or what is the difference between rational number and irrational number? A rational number should contain a recurring decimal digit or a sequence of digits after the decimal. For example, you take the example of 10 by 3. What is this value? If you divide 10 by 3, you would get it as 3.3333, and it continues. This is a recurring number after the decimal. So, if you have such a number after the decimal that is recurring, then you would call this as a rational number. There is also another criteria. It need not be the same number being repeated. It can be a sequence of numbers being repeated. So if you look at the example of 22 by 7, the decimal expansion of 22 by 7 is 3.1428571, 1428571, and you can see that 142857 is getting repeated. Can you see? 142857 is repeated, and it repeats forever. If you expand this, it repeats forever. So even if you have a sequence of repeating digits after the decimal, or a recurring digit after the decimal, it might be the same digit, then in both these cases, you call that as a rational number. Okay? So here, both 10 by 3 and 22 by 7 are rational numbers. Now what are irrational numbers? Irrational numbers are all those numbers which are not rational. That's a very simple definition. But let us understand a bit. Irrational numbers are those numbers that cannot be represented in the form of p by q. By the way, I forgot to tell you one more thing. In the rational numbers is the example of, say, maybe 22.961. Is it a rational number? Yes, it is a rational number. Why? Because you can write it as 22,961 divided by 1000. Right? You can represent this in the form of p by q, right? This is the same value, 22.961. It can be represented as 22,961 divided by 1000, where 22,961 and 1000 are both integers, and you are representing them in the form of p by q, and p and q are both integers. So even this decimal value is also a rational number. You are getting what I am saying? Okay? So when you can represent even a decimal value in the form of p by q, where p and q are integers, then it is a rational number. It can be even minus 22.961. It can be here like minus 22,961 divided by 1000. Both numerator and denominator can be negative integers. It does not matter. They are still rational numbers. Now, when we come to irrational numbers, you cannot represent them in the form of p by q. Let us take some examples. Let us take the example of the number pi. You can see that this is a very great number of digits appearing after the decimal. Can you see? And it doesn't end. You cannot stop this. Pi has after the decimal infinite number of numbers, it still continues like that. So it is impossible to represent pi in the form of p by q, because the decimal never ends. Had it been say 3.14159, then you would have represented this as 314159 divided by maybe 10,000, or like maybe 5 zeros, yeah, maybe 1 lakh. Okay, this would still be a rational number. But however, the decimal number is not, the digits after the decimal are not ending. And again, you can see there is another condition for rationality. If there is a repetition of the sequence of numbers, then you would call it a rational number. But can you see that the numbers or the sequence of digits after the decimal are not repeating anywhere? That is an irrational number. You look at the example of the exponential function. Now, the exponential function, say if you say f of x is equal to e power x, in the expansion notation, it is given as 1 by x by 1 factorial, x power 1 by 1 factorial, plus x power 2 by 2 factorial, plus so on until infinity. This in the short form you can write it as summation I is equal to 0 to infinity x power n by n factorial, right? If you take x is equal to 1, take x equal to 1. Take x equal to 1. Then this will be f of 1 is equal to e power 1, which will be 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial plus so on. And if you add this sum, and this is an infinite sum, friends, it continues without ending. So when you add all those small parts, you will get the value of E as 2.7182818828, and then again say this is not repeating. 828 has come 2 times, but it is not repeating again and again. It has come only 2 times. So if you want to satisfy the condition of recurring sequence of digits, like in that of a rational number, this would be 828, 828, 1828, 1828, 1828, but again it has come only 2 times. It should come again and again, then only we can call it a rational number. But here you see that either the digits or the sequence of digits are not repeating again. Okay, so and then if this continues like that forever, so the number E also cannot be represented in the form of p by q, and that is why it is also not a rational number. Therefore it is called an irrational number. What about the case of root 2? Root 2 also you can represent, and this continues forever. Here also you do not see that the number after the decimal is recurring or the sequence of digits is recurring. So that is why root 2 is also an irrational number. Okay, so now I hope that you understood the difference between both rational numbers and irrational numbers. Let us go forward. What is a real number? Real numbers are the union of both rational and irrational numbers. Now, why are we saying only rational and irrational numbers? Because rational number also contain integers, whole numbers, and natural numbers. Okay? So let us look at the set notation form of all the numbers. Let us see in a nutshell what numbers contain what numbers. Okay? We will start with the natural numbers. Okay? To this, if you add the number 0, you would have the whole numbers. Okay? Now, to this, if you add the negative numbers, then you would have the set of integers. Right? To this, if you add, say, the rational numbers, say like the rational numbers, if you add those numbers that can be represented in the form of p by q, okay, then this will be rational numbers. Right? Now, if you add irrational numbers to this, Okay, then this would be the set of real numbers. This would be the set of real numbers. Can you see that the set of real numbers contain irrational numbers and rational numbers? But rational numbers contain integers, whole numbers and natural numbers. Integers contain whole numbers and natural numbers. Can you see that the real number is the biggest set? It is the entire number system. Okay, and there is a mathematician called Gregor Cantor. He gave a wonderful proof which is beyond the scope of discussion of this lecture. But if you are curious enough, you can go to the internet and Google out the proof given by Gregor Cantor, in which he proved that set of real numbers, I beg your pardon, set of real numbers is uncountable. It is such a biggest number system, you cannot even think. It is uncountable. Okay, so now I hope you understood the difference between natural numbers, whole numbers, integers, rational numbers, irrational numbers, and real numbers. In the set notation form of mathematics, you denote real numbers with the word capital letter R. Let us look at the definitions of division, dividend, divisor, quotient, and remainder. Now, in mathematics, when you talk about division, you will be talking about sharing or grouping a number into equal parts. For example, if I divide 10 by 2, this will give an answer of 5. You would say that when you divide 10 by 2, there will be 5 equal parts. Okay, so that is in essence what is called division. Now, here the numerator is called the dividend. The denominator is called the divisor. And the answer that you get when you divide dividend by divisor is called the quotient. Okay? Now here, because since 2 divides 10 exactly, there is no remainder. Here the remainder is 0. However, take another number. Say 10 divided by 3. This gives the answer as 3. I mean, see, this can be as 3.333, but in mathematics, if you take even the computer programming also, it will give only the quotient. Okay? However, what is the remainder? The remainder is, the quotient is 3, the remainder is equal to 1. Okay? So, you can represent that in the form of an equation. Okay? When you take the divisor and multiply that with the quotient and you add the remainder, you should get the dividend. This is the relationship between dividend, divisor, quotient, and remainder. Let us take an example. If you take 22 and divide it by 2, you will get the answer as 11. Okay, 22 is the dividend here, 2 is the divisor here, 11 is the quotient. Here the remainder is 0 because 2 divides 22 exactly. If you take 45 by 5 again, 9 is the answer, 5 is the divisor, 45 is the dividend, and 9 is the quotient. Again the remainder is 0. Okay? However, if you take the example of say 52 and divide it by 10, you will get the quotient as 5 and remainder as this as the quotient and remainder is equal to 2. Why? Because 10 5s are 50 and because it cannot divide the remaining 2, you take it as the remainder. Okay? So, however, like if you're talking about the quotient, if the quotient is if you are okay with the quotient being a real number, then of course you can simply write it as say 5.2. All right, but when you're talking about the concept of divisor, quotient, remainder, and dividend, you would say that if you divide a number by the divisor, the dividend by the divisor, the answer that you get is the quotient, and if there is a remainder, you will have that remainder. Okay, there are some key points to remember here. The divisor, which is always in the denominator, divides the dividend into equal parts, or into parts and leaves a remainder. Okay, the divisor can divide the dividend either completely or partially. When it divides completely, the remainder is 0. When it divides partially, the remainder is a non-zero integer. And divisor can be a positive or negative number, even the dividend can be a positive or negative number. But please remember, in mathematics, the divisor cannot be a 0 because division with 0 is not defined. Okay, a number that divides an integer exactly, leaving no remainder, is termed the divisor. However, this is the colloquial term being used, which means this is a common term that is used. However, the right term to be used is the word factor. If the dividend gets divided by the divisor, or if a number gets divided by another number exactly without leaving a remainder, then you would call that number which is dividing as the term factor. Again, the divisors 1 and minus 1 can divide every integer present in the number line, including 0. And this is a very unique property of these two integers, 1 and minus 1. Okay, let's proceed further. Let's go for test of divisibility. Now, the test of divisibility by 2 is pretty straightforward. If the unit digits is any of these numbers, either 0 or 2 or 4 or 6 or 8, then you can say that the number will be divisible by 2. Let us take an example. Let us take a very big example. 2, 5, 6, 7, 9, 8, 3. This cannot be divided by the number 2. And 2 is not a factor of this number. Why? Because it ends with this is the unit digit. This is the 10th digit. This is the 100th digit. This is the 1000th digit. This is the 10,000th digit. This is the 1 lakh digit. And this is the 10th lakh digit. Okay? So this is the unit digit. If the unit digit is ending with 0 or 2 or 4 or 6 or 8, then the number is divisible by 2. Let us go to the test of divisibility by 3. A number is said to be divisible by 3 when the sum of its digits is divisible by 3. Let us take an example. Here we are taking an example of 89,613. Right? Let us add the digits. 8 plus 9 is 17. 17 plus 6 is 23. 23 plus 1 is 24. 24 plus 3 is 27. 27 is divisible by 3. When you divide 27 by 3, you would get the answer as 9. Okay. So, since the sum of the digits is divisible by 3 without leaving any remainder, that is the remainder is 0, you would also say that the entire 89,613 also is divisible by 3. So, all you need to have to perform is to add the digits and see if the sum of the digits given is divisible by 3. If it is divisible by 3, then the number is also divisible by 3. What is the test of divisibility by 4? If the last two digits are divisible by 4, then the number is divisible by 4. Let us take an example. Let us take 2, 5, 6, 7, 8, 8. Okay? You look at the last two digits, 88 is divisible by 4. This gives the answer 22. Okay, so this number 256788 is also divisible by 4. There is another condition. If the last two digits are zeros, then also that number will be divisible by 4. Okay, so you can extend this also to the number 25. If the last two digits, if the unit digit and like the 10th digit and the unit digit, if the last two digits of a number are either zeros or divisible by 25, then it is also a number that is divisible by 25. If you look at this example, 28900, the last two digits are zeros, so it is divisible by 25. And because it is also 0 is divisible by 25, last two digits are zeros. Okay, you can write this as, say, okay, let me explain it. Let me not create a confusion in your mind. Okay, so this can be written as 289 into 100, right? If you divide it by 25, 4 into 289 is some number. So this number is exactly divisible by 25. Okay, let us take another example. Let us say 5, 4, 5, 6, 5, 2, 5. Okay, if you look at this last two digits, it ends with 25. So 25 is divisible by 25. Okay, so the entire number 456,525 is also divisible by 25. I hope you got what I am trying to say. The divisibility by 5 is pretty straightforward. If the unit digits number, the unit digit in the given number is either ending in 5 or 0, then you would say that the number is divisible by 5. What about the divisibility by 6? If the number is divisible by both 2 and 3, then it is divisible by 6. What about the divisibility by 8? Here also, what we have looked, the criteria for number 4, if you extend a bit, then you will get the test of divisibility by 8. If the last 3 digits are divisible by 8, or if the last 3 digits are zeros, then the number is also divisible by 8. For example, let us take this. Okay, let us take the example of 256, 459, 256. You take the last 3 digits. Okay, you divide 256 by 8. You would see that this would give the answer 32. It exactly divides, 256 is exactly divided by 8. So this number is also divisible by, because the last 3 digits are divisible by 8, the entire number is divisible by 8. So let us take another example, say 999000. Since the last 3 digits are zeros, the test of divisibility, the condition says it should be either, last 3 digits should be either divisible by 8 or should be zeros. Since the last 3 digits are zeros, the entire 9,99,000, that number is also divisible by 8. The test of divisibility by the number 9, it is the same as the test given for number 3. However, in the case of number 3, the sum of the digits should be divided by 3. In the case of number 9, the sum of digits should be divided by the number 9. Okay, this is pretty straightforward. So test of divisibility by 10, again, if the units digit contains a 0, if the given number ends with a number 0, then you would say that the number is divisible by 10. What about the test of divisibility by 11? It is a little bit tricky, but again, it's very clear if you understand the concept. Let us take the number. Let us take an example here. Suppose you are testing whether this number 32,45,682 is divisible by the number 11. What you need to take? You just need to take the digits at the odd position and the digits at the even position. Okay, let's first number all of them. This is the second number, this is the third number, this is the fourth number, this is the fifth number, this is the sixth number, this is the seventh number, right? So you take the digits at the odd position. You would see 3, 4, 6 and 2 are in the odd positions. You add them. You would see that they add to the sum 15. You take the numbers at the even position. 2, 5 and 8. They also add to 15. Now you take the difference between the odd and even position sums. You would say that the difference is 0. Okay, and 0 is divisible by 15. 15 zeros are 0. So when the difference between the digits in the odd position, sum of the digits in the odd position and the sum of the digits in the even position, when that is a number divisible by 11, then, I beg your pardon, here it should be 11 here. It should be 11. So 0 is divisible by 11. So that is why the entire number is also divisible by 11. So again, it can be 0 or any number, the difference between the sum of the digits in the odd position and the sum of the digits in the even position, when their difference is either 0 or a multiple of 11, then you would say that the given number also is divisible by 11. Here this number 32,45,682, because the sum of the digits in the odd position and the even position are when you take the difference between them, it gives the answer 0. Then also you would say that the number is divisible by 11. It should be either 0 or a multiple of 11. We hope you understood what I'm trying to say. Let us look at the test of divisibility by the number 12. A number is said to be divisible by 12 if it is divisible by both 3 and 4. Let us go to the test of divisibility by the number 14. A number is said to be divisible by 14 if it is divisible by both 2 and 7. Same is the case with the divisibility by 15. If the given number is divisible by both 3 and 5, then you would say that the given number is divisible by the number 15. Again, the test of divisibility by 16, you should extend the test of divisibility for the number 8 a little bit. For number 8, if the last 3 digits are either divisible by 8 or zeros, then you would say that they are divisible by 8. But if the last 4 digits are divisible by 16, then that number is also divisible by 16. Okay, let us take an example. Let us take an example 1, 2, 3, 0, 0, 1, 6. Okay, let us take the last 4 digits. 0, 0, 1, 6. It is definitely divisible by 16. 16 by 16, yes, you will get a quotient of 1. It is exactly divisible. So the number 1, 2, 3, 0, 0, 1, 6 is also divisible by 16 because the last 4 digits are divisible by 16. And the test of divisibility by the number 18, a number is said to be divisible by 18 if it is divisible by 9 and has its last digit either even or 0. In essence, like if the number is divisible by both 9 and 2, then the number is divisible by 18. You can go through the example given here. Now let us look at the definitions of what is a factor, what is a prime number, and what are composite numbers. Now, in mathematical terminology, a factor is any number which when divides another number exactly and leaves a remainder 0, you would call that number as a factor. As I said, the number being divided is the dividend. The number dividing the dividend is the divisor. And when you divide the dividend by the divisor, you have the quotient. And if it divides exactly, you would have the remainder as 0. If it divides partially, you would have some remainder. So when you call a number as a factor, the divisor divides the dividend exactly. Then only you will call that number as a factor. Let us take the example of 72. Now 72 has so many factors. The number 1 is a factor, the number 2 is a factor, 2 36 are 72, 3 is a factor, 4 is a factor, 4 18s are 72, 6 is a factor, 6 12s are 72, 8 9s are 72, 9 is a factor, 12 6 are 72, 18 4s are 72, 24 3s are 72, 36 2s are 72, and 72 also is a factor. Okay. In mathematics, every number has both 1 and itself as factors. And this is not true only for 2 numbers. The number is 0 because 0 is not a factor of itself. And again, 1 is a factor of itself and 1 is a factor of 1. So you cannot count them as twice. You can count them only once. Okay, and this is exactly the definition of what is a prime number. We'll go forward, but let us continue with the example here. 72 has, say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 factors. Here the numbers 1 and 2, the factors 1 and 72, they are called the trivial factors. Okay, because those are the every number except for the number 0 and also the number 1. They have 2 factors, minimum of 2 factors. That is the number 1 and itself. Okay, and this is not true only for in the case of 0 and also 1. You can say, like, because 1 has only one factor. Okay, 1 is a factor of 1 and 1 is a factor of itself, but you don't count them twice, okay, in mathematics. So except for 0 and 1. Okay, now what is a common factor? A common factor of 2 or more numbers is a divisor that divides each of the given numbers exactly without leaving a remainder. For example, you take the numbers 42, 60 and 90. Of course, the trivial factor 1 is always a factor of all these. 2 can divide 42, 60 and 90. Okay, 3 also is a factor. 3 can divide all the 3 numbers. Okay. So you have 1, 2, 3. There can be other factors also you need to check, but I have given the examples of some factors. So 1, 2 and 3 are the factors of the given numbers 42, 60 and 90. There can be more, like you need to test, but definitely these 3 are the factors. They are called the common factors. What are prime numbers? In mathematics, a prime number is any positive integer having exactly 2 factors, 1 and itself. Okay, suppose if I take the number 23, you cannot divide 23 by any number other than 1 and 23 without leaving a remainder, that is having a remainder 0. Okay, let us take an example. Let us divide 23 by 11. 11 2s are 22. So this gives an answer 2, which is the quotient. Okay, and the remainder is 1. Okay, so this is not exactly divisible. So 11 is not a factor. So when a given number has only 1 and itself as the factors, you would call them as the prime numbers. Okay. So any number that does not follow this rule is called a composite number. Okay, which means they can be factored into other positive integers other than, which means in addition to 1 and itself, you will have other factors. Then only you will call that as a composite number. Okay, so here please understand again, what is a composite number? The definition of composite number is any positive integer which has positive factors other than 1 and itself. It means the conditions for primality, that is the existence of 1 as a factor as well as the number itself as a factor. In addition to these two, there should be other factors, which means there should be other numbers which can divide the given number exactly in addition to 1 and the number itself. Okay, then you would call that as a composite number. Okay, merely because a number has more divisors, okay, more divisors like or more than 2 divisors, it does not mean that the number is a composite number. We will see that in the example of 0. 0 is having infinite number of factors. If you divide 0 by any number in the number system, any real number in the number system except for the number 0, every number in the number system except for the number 0 can divide 0. Okay, but that is a very essential condition. A number can be only called composite if it is in addition to not only being a factor of, not only having a factor 1 as a factor and itself as a factor, it should have other numbers as a factor. So the essential condition is 1 should be a factor, the number itself should be a factor of itself. In addition to that, there should be other factors. Then you call it as a composite number. Okay. Now let us look at the examples of why 0 and 1 are not called either composite or prime. Okay, let us look at that. First of all, let us look at this definition. Okay, let us look at these two definitions. Let us have a definition, glance at these two definitions. Prime numbers, they say prime numbers, the definition says that prime number is a positive integer having exactly 2 factors. Okay, that is 1 and itself. It should be a positive integer. It should have only 2 factors, 1 and itself. Okay, and let us look at the definition of composite number. A positive integer which has positive factors other than 1 and itself. In addition to 1 and itself, there should be a positive factor, and then it is called a composite number. Let us look at this explanation. Okay, let us look at why 0 and 1 are not prime or composite. Let us take the number 0. Why is it not prime? The first condition is it should be a positive factor. But 0 is neither positive nor negative. Right? What is the second condition? Let us call this as A. What is the second condition? Let us call this as B. The second condition for primality is 0 should have 1 as a factor. Of course, that condition is satisfied. 1 can divide 0. and 0 should be divided by itself. This condition is not satisfied. 0 by 0 in mathematics is not defined. So, when this condition is not satisfied, the test of primality fails. Test of primality says that it should be a positive factor. There also it got failed. And there should be exactly two factors, the factor 1 and also the number itself. 1 is a factor which the condition is true for 1, but 0 is not a factor of itself. So that is why 0 is not prime. And why is 0 not composite? Why is 0 not composite? Why? Because conditions of primality, that is existence of exactly two factors, 1 and itself. In addition to that, if there are other factors, then you would call composite. Okay, let us look at this first. Is 0 having any other factors? Yes, you divide any number by 0. I will call this, say, x. X can be any number in the real number system except the number 0, because 0 by 0 is not defined. All those numbers can divide 0. So 0 has infinite number of divisors. So this condition is satisfied. However, in addition to that, the condition of primality should also be satisfied, which means other factors, there are umpteen number of factors. 1 also should be a factor. Yes, 1 is a factor, but 0 is not a factor of 0. Okay? So 0 is not composite because 0 is not a factor of itself. Okay, it has umpteen number of other factors. All the numbers except for 0 in the number system are factors of 0. However, 0 is not a factor of itself. That is why 0 is also not composite. We will also discuss why 0 is not composite from the standpoint of prime factorization theorem, which is also called the fundamental theorem of mathematics. But we will come to that in a moment later. Okay, so I hope you understood why 0 is neither prime nor composite. Let us look at the aspect of the primality or compositeness of the number 1. Okay, let us look at that. Why, along with 0, 1 is also neither prime nor composite. Let us look at the definition of 1. Okay, again the condition is it should be a positive factor. 1 is a positive number, there is no doubt about it. Okay, so this condition is satisfied. And what is the second condition? It should have exactly two factors. One of the factor is 1. Yes, it is a factor. The other factor is itself. Okay, of course this is also true, but they cannot be counted as two factors. They can be counted as only one factor. Okay, you cannot take 1 and 1. Why? Because it fails, because it can be represented as a unique representation of prime factors. That is why, and this is because of the fundamental theorem of mathematics, which will come a little bit later. That is why you cannot count 1 twice. Okay, 1 is a factor and 1 is a factor of itself. 1 is a factor of 1, 1 is a factor of itself. However, you cannot count them twice. Okay, that is the reason why it is not prime. Okay, and why is it not composite? Again, the condition of compositeness, it should be condition for primality plus other factors, right? Here condition for primality is also failed. Why? Because there is only one factor of 1, that is itself. Okay, you cannot count it twice. And are there any other factors of 1? Okay, other than 1? No, there is only one factor of 1, that is 1 itself. Okay, so there are no other factors of 1, right? So that is why test of compositeness fails for 1. We hope you understood the concept of why 0 and 1 are not prime or composite. Okay, we will also discuss the same from the standpoint of the fundamental theorem of mathematics in a short while. Okay, there we will see why 1 and 0 are not composite. Okay, what are coprimes? Coprimes are those numbers, okay, who have or which have their highest common factor. We will see what a highest common factor is. Okay, so if the numbers have their highest common factor, only one is the highest common factor, then you would call those numbers as coprime. Okay, for example, if you take the numbers 2 and 3, you would see that the highest common factor of both 2 and 3 is the number 1, and other than 1 there are no other common factors. Forget about highest, there are no common factors between 2 and 3. Okay, so it is the only factor and it is the highest common factor. Then we can say that they are coprimes. Here 2 and 3 are coprimes. Similar is the case with 7 and 8. The highest common factor for 7 and 8 is only 1. Okay, so that is why 7 and 8 are called coprimes. What are even numbers? And this is a very straightforward definition. If the units digit in a given number has 0, 2, 4, 6 or 8, then you would call it as even numbers. If it has 1, 3, 5, 7 or 9, then you would call it as an odd number. Okay, now let us come to the principle of prime factorization. It is also called the fundamental theorem of mathematics. What is this? It states, okay, let us, even before stating that, let us go into the first bullet point. Any natural number that is greater than 1 is either prime or composite. This is true for any natural number greater than 1. It is not true for 1, it is not true for 0. Okay? Now, what does the principle of prime factorization state? It states that every integer greater than 1, please put emphasis on this phrase, every integer greater than 1 is either a prime number itself or can be represented as the product of prime numbers, and such representation is unique if you ignore the order in which the factors are present in the prime factorization. Let us take an example. Okay, let us take the example of, say, 80. You can write 80 as 2 into 3 into 3 into 5. 2 3s are 6, 6 3s are 18, 18 5s are, I think you could take the number as 90. I'm very sorry. Let's take the number as 90. I've taken this example. I've taken this example to give you an example with different types of factors. Okay. Now this can be written as 3 into 2 into 3 into 5. This can also be written as 3 into 3 into 2 into 5. This can also be written as 3 into 3 into 5 into 2. This can also be written as 5 into 2 into 3 into 3. This can also be written as 5 into 2 or 3 into 2 into 3. Can you see that all of these products will yield the number 90? Okay? However, if you ignore their order, you can represent the number 90 as a product of only 1 2, 2 3s and 1 5. Okay? This is the unique representation that we are talking about. What does principle of prime factorization says? You can represent every number greater than 1 is either a prime number itself. Let us take the number of say maybe 23. 23 is a prime number itself. Let us take 17. 17 is a prime number itself. Let us take the number 18. You would say 2 into 3 into 3. Right? So, every number greater than 1 in the number system is either a prime number itself or can be represented as a product of prime numbers. Can you see when you have reduced the number 90 as a product of prime factors, can you see that 2 is a prime number, 3 is a prime number, and 5 is a prime number? So you can reduce any number greater than 1, which is, it should be either prime, and if it is not prime, it should be composite. And if it is a composite number, then it can be reduced as a product of prime numbers. And if you ignore the order in which that prime numbers are multiplied, then this, such representation is a unique representation, which means if you take 90, it is a product of only 1 2, 2 3s, and 1 5. If you take 18, it can only be represented as a product of 1 2 and 2 3s, and not otherwise. Okay, now I hope you are getting a hang of this word unique. When we say that such representation is unique, we say that other than these prime numbers, factors of other than multiplication, the product of these prime numbers, you cannot represent 90 in any other way. If you ignore the order in which they are multiplied, all of them are same in multiplication, because multiplication is I think associative, commutative, all those properties hold good for multiplication. So if you ignore the order in which they are multiplied, then you would see that such representation of a composite number as a product of prime factors, that is unique. Okay, so I hope you are getting what I am trying to say. Okay, so with this principle, a composite number can be broken into its prime factors by dividing it with different prime numbers. We'll look at that. Okay, this is also known as the division method of factorization of a number. I have given a number here. You can try with the example of 330. It can be reduced into a product of prime factors as 2 into 3 into 5 into 11 in the common parlance, when we deal with reducing a number into a product of prime factors, we start with the lowest prime factor and proceed forward with the next highest and next highest prime factor. Okay, so it can be represented, 330 can be represented as a product of 2 into 3 into 5 into 11. Okay, and this representation is unique. Okay, now let us look at some of the important properties of prime numbers. Every number greater than 1 can be divided by at least one prime number. Let us take the example of 29. It can be divided by 29, which is a prime number. Let us take the example of 104, right? It can be divided by 2, which is a prime number. You take any other number. You take, say, 111, okay, 1. I think it should be divisible by a prime number. Let us see what is that prime number. The sum is 4, right? Say, okay, let us take another example. I think I just need to find it out. It holds good. Let us take the digits of 111. This is divisible by 3, right? Because the sum is 3. When you divide it by 3, it will be 3 3s are 9 and 3 7s are 21. Okay, it gives the quotient as 37. You can try it with other numbers. Even the number 1111 also will be divisible by a prime number, but we have to find out. It is difficult. Probably you can try it for yourself. Okay, this holds good. Every positive integer greater than 2 can be expressed as a sum of two primes. Let us take the number 42. In what way can we represent this as a sum of two primes? I think 19 plus 23, the sum is 42. Yes, it is 42. Okay, you take, say, maybe 18. Okay, sum of two primes, 11 plus 7. So this also holds good for every positive integer greater than 2. What is the third point? Except 2, all other prime numbers are odd. In fact, 2 is in the entire number system, 2 is the only prime number. Sorry, even prime number. 2 is the only prime number that is even. In the entire number system, it is the only number that has that property. Okay. And then the next point is, we have discussed this is the definition of co-primes. Okay, so if you take a prime number and composite number, okay, then you can see if they have the highest common factor as 1, then they are called co-primes. But necessarily two prime numbers are always co-prime to each other. Okay. The fifth point is, each composite number can be factored into prime factors, and individually all of these are unique in nature. Oh, this is nothing but the prime factorization theorem. Okay, this is the fundamental theorem of mathematics. We've discussed that. Now, let us discuss about, from the standpoint of prime factorization theorem, why 0 and 1 are not composite. Okay. Now, what is the test of compositeness? The test of compositeness says that every number, okay, a number is said to be composite if it satisfies the condition of primality, that it has two factors, okay, one in itself. Along with that, it has other factors, okay. And if you take the fundamental theorem of mathematics, what does it say? It says that every integer greater than 1 is either a prime number itself, or it can be reduced into or represented in the form of a product of prime numbers, and such representation is unique. Let us now take the example of 0. Okay. Now, why 0 fails in satisfying the fundamental theorem of arithmetic? Okay. So, let us take how 0 can be represented. If you take 0 as a product of 0 into 2 into 3, this is also 0. If you take 0 as product of 2 into 3 into 5, this is also 0. You can also take 0 as a product of 2 into 3 into 5 into 7 into 11. This is also 0. What does the fundamental theorem of mathematics say? It says that if the number is composite, it can be represented as a product of prime numbers, and such representation is unique. However, all these products are zeros, but their representation is not unique. In the first case, it is 0 into 2 into 3. In the second case, it is 0 into 2 into 3 into 5. In the third case, it is 0 into 2 into 3 into 5 into 7 into 11. All these three are three different representations. It is not unique. So, 0 does not satisfy the fundamental theorem of mathematics, and hence it is not composite. I hope you are now trying to appreciate the application of fundamental theorem of mathematics in proving that 0 is not a composite number. Okay, same is the case with 1. Let us take the example of 1. Okay, now what is 1? 1 is 1. 1 can be represented as 1 into 1 into 1, or 1 into 1 into 1 into 1 into 1. Can you see? All of them are ones. Okay? And these representations are not unique. Here you have multiplied 5 ones, here you have multiplied 3 ones, here you have represented 1. And all these equations are true. But these are not unique representations. Okay? So can you say 1 is a factor, 1 is a factor, 1 is a factor, but you cannot count 1 more than once. And then it says that it can be represented as a product of prime numbers, and 1 is not a prime number. Okay, 1 is not a prime number, and further, even if assuming but not admitting that 1 is a prime number, such representation is not unique. Okay, so for these conditions, for the condition of 0 and 1 failing to satisfy the test of fundamental theorem of mathematics, which means that 0 and 1 cannot be represented as a product of prime numbers and cannot be represented in a unique manner, they are not called composite numbers. Okay, I hope you understood now from the standpoint of fundamental theorem of mathematics why 0 and 1 are not called composite numbers. Let us move forward. Let us understand the concepts of H.C.F and L.C.M. Now, H.C.F is the abbreviation for highest common factor. And please, in mathematics, I would suggest Almost all of the terms used in mathematics are self-explanatory. When you read the words involved in a particular term, they explain for themselves. When you say highest common factor, the first thing is you go in the reverse direction. Okay? You go in the reverse direction. What is the first condition? It is a factor. Means it is a number in the denominator. Means when you say that a number is the highest common factor of few other numbers, then that number, what is the condition of a factor? When would you call a number as a factor? When a number divides another number exactly with leaving a remainder 0 or without leaving any remainder, then you would call as factor. So the highest common factor is first a factor. Okay, it is a number in the denominator. If you extend a bit, what is that? It is there. It is the common factor, which means when you are calculating the highest common factor, say if you are calculating the H.C.F of 2 or 3 numbers, okay. Now say, let us take the example of 3 numbers. If you are calculating the highest common factor for 3 numbers, first of all it is a factor, which means it divides all the 3 numbers exactly, and it is a common factor, which means, sorry, when you say it is a factor, it divides each of these numbers, and when you say common factor, it divides all the 3 numbers, okay. And when you say highest common factor, when you move a bit forward, when you say highest common factor, it means among the factors of all the numbers for which you are calculating the H.C.F, okay, the H.C.F is the highest factor, highest common factor. Okay, we will look at examples, which it will make your life a bit easier. Okay, we will look at examples, and I hope you understood. It should be a factor, it should be a common factor, and it is the highest common factor. Okay, it is the highest among the common factors. It is also called as the greatest common measure or the greatest common divisor. Okay, so these are the other terms used for H.C.F. Now there are two methods of calculating the H.C.F. One is called the method of prime factors. The other one is called the method of division. We'll look into them. Okay. Now we look at the method of prime factors. Now what does method of prime factors do? Like how would we calculate the H.C.F using this method? If two or more numbers are broken into their prime factors, how can you break them into prime factors? The fundamental theorem of mathematics says so. Every number greater than 1 is either a prime number itself, or it can be represented as a product of prime numbers, and such representation is unique. So it guarantees that every number greater than 1 can be represented as a product of prime factors. So every composite number or every number can be reduced into a product of common prime factors. Okay. So then if you reduce them into prime factors, then the product of the maximum common prime factors, please look at this sentence, the product of the maximum common prime factors, that is the H.C.F. Okay, that is the H.C.F. Now let us take an example. Let us take the example of calculating the H.C.F of 108, 288 and 360. Now from this example, let us understand the meaning of product of maximum common prime factors. Okay. First, let us reduce each of these numbers into a product of their prime factors. Now what are the factors of 108? 108 is, if you reduce them into prime factors, it is a product of 2 into 2 into 3 into 3 into 3. Okay. It is a product of 2 2's and 3 3's. So let us just understand that we have reduced it properly. 2 2's are 4, 4 3's are 12, 12 3's are 36, 36 3's are 108. Yes, we have reduced it properly. What are the factors of 288? It can be represented as a product of 5 2's and 2 3's. What are the factors of 360? It can be represented as a product of 3 2's, 2 3's and 1 5. Okay. Now let us first examine what are the common factors among them. You see, 2 is a common factor. Can you see that 2 is a common factor in all of them? What is the next common factor? 3 is the common factor. What about 5? 5 is present as a factor of only 360 but not in 288 or 108. So this is not a common factor. So ignore 5. Now it says, now let us look at what are the common prime factors. We have discussed that 2 and 3 are the common prime factors. Now what are the maximum common prime factors? Okay. Now you look at this, 2 square is present here. Okay. Now 2 power 5 can be written as 2 square into 2 cube into 3 square. So 2 square is present here also. What about this one? Now this can be represented as 2 square into 2 into 3 square into 5. So 2 square is present here also, right? So you take 2 square as the common prime factor, okay? And it is the maximum common prime factor that is present of 2, that is present in all the 3 numbers, okay? Now let us look at the number 3, okay? Now this can be represented as 2 square into 3 square into 3, okay? So what is the highest power of 3 that is common in all the 3 numbers? 3 square is common here, 3 square is common here, 3 square is common here. So the maximum common prime factors, if you ignore, like if you, forget about the powers here, okay? 2 and 3, and if you take the powers, because we are taking the maximum common prime factors, you see that 2 square is common in all the 3 numbers and 3 square is common in all the 3 numbers, okay? So the product of the maximum common prime factors in this case will be 2 square into 3 square, which is 4 into 9. So 36 is the HCF of highest common factor of 108, 288 and 360. Okay. So let us examine why 36. Are there any other factors other than 36? Yes, there are factors. In fact, the number 2 divides all these 3. 2 54s are, 2 144s are, 2 180s are. And even the number 3 also divides, say 108, you can say 336 are 108. And if you take 288 divided by 3, you would say 96, 396 are 288 and 3 120s are 360. Okay, so you can have even, I think even maybe the number 12 also. Yes, even number 12 also is a factor of all these 3 numbers. 12 nines are 108, 12 24s are 288 and 12 30s are 360. Is it so? Let us just verify that. Yes, 12 30s are 360, right? However, you would see there are many number of factors for all the 3 numbers. There are many common factors for all the 3 numbers. 2 is a common factor, 3 is a common factor, okay, 12 is a common factor. You can check if 4, and maybe 6, all of them are common factors. But among those factors, only 36 is the highest common factor, which means among the factors of all the 3 numbers, 36 is the highest common factor, and there will be no other factor greater than 36 that can divide all 3 of them exactly. Okay, so with this example, I hope you are clear with the concept of, why we are saying highest common factor. It is a factor. Second thing, it is a common factor, and it is the highest common factor. And there will be no other number greater than that number, which is a factor of all the 3 numbers or all the given numbers for which you are calculating the HCF. Okay. Now let us look at method of division of calculating the HCF. Okay. What does it say? Suppose we are calculating the HCF of 42 and 70. Let us first divide 70, which is the bigger number, with 42, which is the smaller number. So 70 is the dividend, 42 is the divisor here. If you take 42 once, 42, the remainder is 28. Now you carry forward this divisor here, okay, and try to divide it again. 28 ones are 28, and if you take 28, the remainder is 14. And you carry forward this divisor here. Now 14 twos are 28. You see, this 14 divides 28 exactly. So this divisor, when you continue this division, the divisor that the last divisor that divides the remainder exactly, leaving a remainder 0, that is the HCF. So you can see that the Number 14 is the highest common factor of 42 and 70. Okay. Is there other common factor? Yes, there is. Even 7 divides 42 and 70 also. Right? This is 7 6 are 42 and 7 10s are 42. But this is not the highest one. Which one is the highest one? 14 is the highest one. Okay. There may be common factors which are lesser than the HCF that may divide the given numbers. But there will never be a bigger number greater than the HCF that can divide all the given numbers exactly. So that is the concept of HCF. And this is the method of division using two numbers. Let us look at the method of division using more than two numbers. Okay. So let us first try to find out the HCF of the number 1365, 1560 and 1755. Okay. Now first take the lowest of these numbers and take the next highest number. So treat the lowest number as the divisor and the next highest number as the dividend, and try to divide them and try to find out the remainder. So you see that when you multiply 1365 by 1, you would see that you will have a remainder of 195. Now you carry forward this divisor here and you would see that 195, if you multiply that with 7, you would get the answer 1365. So this leaves a remainder 0. Okay. So the HCF of 1365 and 1560 is 195. Okay. Now what you can do is, immediately you see if this number 195 divides the other number. Okay. If it divides, then 195 is the highest common factor. Okay. If it doesn't, then follow the method of division for 195 and the remaining number and try to find out the highest common factor. In this case, the number 195 divides 1755 exactly. If you multiply 195 by 9, you would get 1755 and the remainder is 0. Okay. So the HCF of 1365 and 1560 is 195. The HCF of 195 and 1755 is also 195. So the HCF of all the three numbers is also 195. Okay. Now I hope you understood how you can calculate the HCF of more than two numbers. Okay. Now how do you calculate the HCF of smaller numbers? If the given numbers are smaller, then there is a very simple route. Okay. Now first take the, let us take the example of calculating the HCF of 21, 15 and 36. Now what is the HCF of this number? Let us start with the smallest number. What is the smallest number? 15 is the smallest number. Okay. If you reduce 15 into prime factors, what are the factors of 15? So when you say factors of 15, you would say 1 is a factor of 15, 3 is a factor of 15, 5 is a factor of 15, 15 is a factor of 10. So 1 is the lowest factor, 15 is the highest factor. Okay. So you try to see if 15 divides the other numbers. If it divides, then 15 is the highest common factor. If it doesn't, then go to the next highest factor. In this case, the next highest factor of 15 is 5. See if 5 divides 21 and 36. It doesn't. So go to the next highest factor. See if 3 divides 21 and 36. Yes, 3 divides 21 and 36. So the highest common factor of 21, 15 and 36 is the number 3. So if you have very small numbers, you start with the smallest number, look at the factors, divide the other numbers with the smallest numbers, and then if it doesn't divide, and go one step down and look at the next highest factor and next highest factor and see which factor divides the other numbers. And that factor that divides the other numbers is the HCF. Okay, I hope you understood this concept of calculation of HCF using this technique for small numbers. Now how do you calculate the HCF of decimals? Okay, let us take the example of we are taking this is a very less font, very small font. So I'll write those numbers. We want to calculate the HCF of 16.5, 0.45 and 15. Okay. Now let us represent these three numbers in, okay, let us multiply with this with a suitable base 10 in order to make them whole numbers. Okay, and it should be the number should be, each of these numbers should be multiplied the very same base 10. Okay, so here we want to eliminate the decimals. So because if I want to eliminate the decimals 0.45 and make it a whole number, I have to multiply this by 100. So I have to multiply this also by 100 and this also by 100. So when I multiply, first step is multiply by 100. So these numbers will be 1650, 45 and 1500. Okay. Now calculate the HCF of these three. Okay. So you can use the method of division. Now first take 45 and 1500. Now when you multiply 33 times, it will give you 1485 and the 15 is the remainder. And when you take the divisor 45 here, 15 3s are 45 and leaves the remainder 0. So the HCF of 45 and 1650 is 15. Okay, now calculate the HCF of 15 and 1650. Okay, as you can see, this number 15 divides 1650 exactly. Why? 15 hundreds are 1500, 15 tens are 150. If you add 1500 and 150, it will give you 1650. So when you divide 1650 by 15, this will be 110. Right? So the HCF of 1650 and 15 is also 15. Because 15 divides 1650 exactly. So HCF of 45 and 1650 is 15 and HCF of 15 and 1650 is also 15. So the HCF of all these three numbers 1650, 45 and 1500, HCF of 1650, 45 and 1500 is 15. But this is not the answer. Why? Because you have bloated these numbers. You have multiplied these numbers with 100. So the answer needs to be divided by 100 to get the HCF of these decimals. So therefore HCF of 16.5 comma 0.45 and 15 is 15 by 100, which is 0.15. This is the HCF. So I hope you understood the concept of calculating HCF for decimals. Okay, let us now go and try to see how we can calculate HCF of fractions. Okay, so what is the HCF of two or more fractions? It is the highest fraction which exactly divides each of the given fractions. Okay, and there is a formula also, but follows these steps. Okay, so in some cases the fractions may be given in not the simplified form. Suppose if I am asking, try to find out the HCF of say 54 by 9 and this is a mixed fraction 3, 19 by 17 and 36 by 15. Can you see that this is not the simplest form? 54 by 9 is 6 by 1. So reduce them into their lowest terms. Okay, and then use this formula. HCF of fractions is HCF of numerators divided by LCM of denominators. Okay, we will see what an LCM is, but for now let us take this example and let us please assume that whatever I am telling in terms of calculation of LCM is correct. Okay, but we will see that in a short while. Okay, so let us take an example here. What is the HCF of 54 by 9 and 319 by 17 and 36 by 51? Let us take these three numbers. Okay, let us take these three numbers. 54 by 9 and 319 by 17 and 36 by 51. Okay, if you reduce it in the simplest form, this will be 6 by 1. This will be say 51 plus 19 is 70 by 17. So let us take this as 9, okay, because I think now I have missed that. Okay, So let us take this as 9, okay? Let us take this as 9. So let us take this as 9, because I have to recalculate again. So this is 60 by 17. Okay, and this is 36 and 51 can both be divided by 3. So this is 3 12s are and 3 17s are. Okay, so these are the fractions in the lowest terms. Now what is the HCF of these fractions? Calculate the HCF of the numerators. What is the HCF of 6, 60 and 12? You can calculate by either of the methods, method of prime factors or method of division. So you can see that the HCF of 6, 60 and 12 is 6. What is the LCM of 1, 17 and 17? 17 is the LCM, lowest common multiple. So the HCF of 54 by 9, 3, 9 by 17 and 36 by 51 is 6 by 17. This is the way you would calculate the HCF of fractions. Now there is an important point here. The HCF of a fraction is always a fraction, but this is not true with LCM. It need not be a fraction. Okay. Let us now go to the concept of LCM. Now again, let us try to understand what is the meaning of multiple, common multiple, and then let us go to the definition of lowest common multiple. Okay. When you say a common multiple, that two or more numbers as a common multiple, then that number is a number which is exactly divisible by each of the numbers for which you are calculating the common multiple. Okay. For example, let us take the common multiple of 2 and 3. What is the common multiple of 2 and 3? Okay. 6 is the common multiple of 2 and 3. 12 is the common multiple of 2 and 3. 18 is the common multiple of 2 and 3. 24 is the common multiple of 2 and 3. 30 is the common multiple of 2 and 3. 36 is the common multiple of 2 and 3. So you can go on. Okay. However, when we come to the concept of lowest common multiple or least common multiple, so by the way, like, what is the common multiple? I mean, where should it be present? When you are saying common multiple, it is the dividend, meaning it is that number which gets divided by 2 and 3 exactly. So when you take the common multiple as the numerator and divide by the numbers for which you are calculating the common multiple, then the common multiple should be exactly be divisible by the the numbers for which you are calculating the common multiple. Suppose here the common multiple of 2 and 3 is 6. When you divide by 2, this is exactly divisible. When you divide by 3, this is exactly divisible. Okay. So when you are, so what is the difference between HCF and LCM? When you are talking about the HCF, it is the number in the denominator. It is a factor. Okay. But when you are talking about the common multiple, it is the number in the numerator. It is the dividend. Okay. So we understood the concept of common multiple. Then what is the lowest common multiple? The lowest common multiple of two or more numbers is the lowest of the numbers which is exactly divisible by each of them. Okay. So it should be a common multiple and it is the least such common multiple. Okay. If you take the example of finding the common multiple of 2 and 3, you can see that 6 is a common multiple of 2 and 3, 12 is a common multiple of 2 and 3, 18 is a common multiple of 2 and 3, but among them 6 is the lowest such common multiple. You can have umpteen number of common multiples, okay, above 6. However, you cannot have any common multiple below 6 that gets divided by both 2 and 3 exactly. That is the meaning of least common multiple. It is the lowest common multiple. Okay, let us take the examples. You can see that the common multiples of 3 and 5 are 15, 30, 45, 60, 75, 90, which means 15 gets divided by 3 and 5, 30 gets divided by 3 and 5, 45 gets divided by 3 and 5. Similarly, 60, 75, 90 also gets divided by 3 and 5. However, which among this is the lowest? 15 is the lowest. And that is why you call 15 as the lowest or the least common multiple of 3 and 5. Okay, similar to LCM, there are also two H.C.F. There are also two methods for calculating LCM. Let us look at those two methods. The first method is the method of prime factors, and the second method is the method of dividing by common prime factors. Let us look at the first method. Now, when you are asked to calculate an LCM of certain numbers, first of all, reduce those numbers into a product of prime factors. Okay? Now, how would you calculate the LCM based on this product of prime factors? The LCM is the product of the highest powers of all the factors. Remember, in H.C.F. example, we took three numbers in which two numbers have 2 and 3 multiple various varying powers of 2 and 3 as factors, but in the third number there is a 5. So in calculation of H.C.F. we ignored that 5. However, in calculation of LCM, we should include all the factors, even if they are not common. Okay? So, it is the product of the highest powers of all the factors that occur in the given numbers. Let us take an example. If you are asked to calculate the LCM of 18, 24, 60 and 150, let us first reduce them into product of prime factors using the prime factorization theorem. 18 can be reduced into 2 into 3 into 3, simplified form 2 into 3 square. 24, 2 cube into 3. 60, 2 square into 3 into 5. 150, 2 into 3 into 5 square. Now what are the factors here? So here we are not talking about we are not talking about the common factors. We are not talking about the condition of the factors being present in all the numbers. We are considering all the factors present across all the numbers. What are all the distinct factors here? Here only 2 and 3 are factors, varying powers. Here 2 and 3 are factors. Here 2, 3 and 5 are factors. Here also 2, 3 and 5 are factors. Okay. Now let us consider the highest powers of 2 in all of them. What is the highest power of 2 here? 2 cube is the highest power of 2. Next will be the highest power of 3. 3 square is the highest power of 3 here. Okay. Now the highest power of 5. 5 square is the highest power of 5. Okay. So in order to calculate the LCM, you need to take all the factors with their highest powers and take their product. So what is this product? This product is 2 into 2 is 8 into 9 into 25. So this is 8 nines are 72, right? Okay, 72 into 25. Okay, this will come as 1800. So the LCM of 18, 24, 60 and 150 is 1800. The lowest common multiple of all these numbers is 1800, which can be exactly divided by all these numbers. If you take it into 2, this is also a common multiple. If you take it instead of 2, you take it into 3, 1800 into 3. So if you take 3600 or 5400, all these numbers gets divided by all these numbers. However, 1800 is the lowest common multiple. Okay, so and then there is no number lesser than 1800 that can get divided by all these numbers exactly. Which means if you take all these numbers, suppose if there is there will be no number less than 1800 which gets divided by all these three numbers exactly. Meaning, there exists no number lesser than 1800, no number lesser than 1800, okay, gets divided by 18, 24, 60 and 150. Okay, this is the least of such numbers. But there will be, if you take numbers greater than 1800, yes, there are umpteen number of numbers. 3600 also gets divided by all these numbers. 5400 also gets divided. Okay, a lot of other numbers gets divided. Maybe even, I don't know, you have to search for it. But a number less than 3600, if it is common, that can also get divided by all the numbers. But 1800 is the lowest such number, and that is why it is called the LCM of 18, 24, 60 and 150. Okay. Now, what is the method of dividing by common prime factors? You just have to write down all the given numbers in a line separating them by commas. Okay. And then what should you do? You need to start dividing starting from the lowest prime number 2, 3, 5, 7. Start dividing because fundamental theorem of mathematics says that every composite number can be reduced into a product of prime factors, right? So there will definitely be, every number can be represented so, okay, whatever number you take, composite number, that can be represented as a product of prime factors. So first of all, write down all the numbers in a line separated by commas, then try to divide them by using prime numbers 2, 3, 5 and 7, okay, and then what all numbers which did not get divided, carry it forward below and repeat the process, okay, until you get a line of numbers which are prime to one another. Okay, the product of all the divisors and the numbers in the last line will be the required LCM. Okay, now in order to simplify your work, at any stage of the process, if any of the numbers is a factor of any other number in the same line, then you can strike them off. We will take an example. Here we are asked to find the LCM of 12, 15, 90, 108, 135, 150. Okay, now we talked about a tip that if any of the number is a factor of any other number in the same line, then you can strike it off. You can see that 12 is a factor of 108 and 15 is a factor of 90. You can strike them off. Okay, so I struck them off. Fine. Now you carry forward the remainder. Why are we doing so? Because when you take the factors for 90 and 108, obviously the factors for 12 and 15 also will come. Okay, so you don't need to do them separately. It is like, Herculean task. You can reduce that number of steps by simply striking those numbers which are factors of other numbers in the given line. Okay, so since 12 is a factor of 108 and 15 is a factor of 90, I struck them off. Okay, now start with the factor 2. 2 45s, 2 54s, 2, because 135 cannot be divided by 2, I carry that below. 2 75s are 150. Okay, now because you look at these numbers 45, 54, 135 and 75. Because 45 is a multiple of 135, I strike 45. And now all of them seem to be multiples of 3, right? So I take, and they are not multiples of 2, so that's why I cannot take 2. So I take multiples of 3. Okay, so I use 3 as a number and try to take those multiples. So 3 18s are 54, 3 45s are 135 and 3 25s are 75. Again, these three maximum numbers are actually divisible by 3, so I take 3 again. 3 6s are 18, 3 15s are 45, and because 25 cannot be divided by 3, I carry it forward. Now because maximum numbers can be divided by 5, I take 5 and I carry forward 6 because 6 cannot be divided by 5. And here 15 and 25 because they are divisible by 5. 15 3s are 5 3s are 15 and 5 5s are 25. Okay. Now you can see that 3 is the factor of 6. So I strike off 3. And you can see that 5 and 6 are here. 5 and 6 are co-primes. Okay. So we have to stop the process here. Now, how do we calculate the LCM? We said it should be the product of all the divisors and the co-primes. Okay? Now, what is the product of all the divisors and the co-primes? 2 into 3 into 3 into 5. This is the product of all the divisors. Okay? Into 6 into 5. Product of co-primes. Okay? So, please calculate the product now. 2 3s are 6, 6 3s are 18, 18 5s are 90, 96 are 540, and 545s are 2500 and 2700. So 2700 is the least common multiple that can be divided exactly by 12, 15, 19, 90, 108, 135, 150, which means there is no number less than 2700 that can get divided by all these numbers exactly. There are umpteen numbers, there are infinite numbers present, that are greater than 2700. So if it is 2700, you can say 2700 into 2, 2700 into 3, 2700 into 4, all of them can get divided by all these numbers. However, there is no number lesser than 2700 that can get divided by all these numbers. So this is the lowest common multiple. Okay? So I hope you understood these two methods of calculating the LCM. Okay? Now, similar to the H.C.F, how do you calculate the LCM of decimals? Now, first of all, let us take an example. If you want to calculate the LCM of decimals, then first multiply them with a suitable power of 10. So, because because there are two decimal places here, I would multiply each of these numbers by 100. So, I would make them as, say, if I multiply them 100 by 100, then these numbers will be 60, 960 and 36. Okay. Now, you need to calculate the LCM of these three numbers. Now reduce them into factors. This is 2 square into 3 into 5. This is 2 power 6 into 3 into 5. This is 2 square into 3 square. Okay. So, what is the LCM here? You need to take the factors here now. Now, 2 is a factor. What are all the distinct factors? 2 is a factor. 3 is a factor. 5 is a factor. What is the highest power of 2 here? 6 is the highest power of 2. What is the highest power of 3 here? 2 is the highest power of 3. What is the highest power of 5 here? 5 is the highest power of 5. So this will be 64 into 9 into 5. Right? So this will be 2880. Right? But since you have bloated this number by a factor of 100, you need to divide that by that very factor to get the answer for the decimals. So since, okay, 2880 is LCM of 60, 960 and 36. So 2880 divided by 100 is equal to 28.80 is the LCM of, therefore LCM of 0.6, 9.6 and 0.36. Okay, it is as simple as that. Now let us just spend some time. This is the method of calculating, LCM. Let us again recall. Let us see, how much you remember the concept of HCF. Now, if you have to calculate the HCF of these three numbers, 60, 960 and 36, what will be the HCF? Okay, what are the common factors? Okay, 2 is a common factor, 3 is a common factor, 5 is not a common factor here. Okay, 5 is not a common factor here. So we take both of them. And what are the common factor of 2 here? It can be written as 2 power 2, it can be written as 2 square. So 2 power 6 can be written as 2 power 2 into 2 power 4. So 2 square is also common here. 2 square is also common here. So 2 square is a common here. If you look at 3, so 3, this is 3 square, so it can be written as 3 into 3. There is a 3 here, there is a 3 here. So there is a 3 common here. Okay. So can you see, this is 4 into 3. This is 12. Okay. 12 is the highest common factor of all these three numbers. Okay, so now you understood, if you are calculating the HCF, look at first the common prime factors, okay, and take the lowest of the powers, okay. If there are no common prime factors in all the numbers, you need to ignore those numbers, okay. So you take the lowest of the prime factors that are common in all and multiply them. But in the case of LCM, you need to take all the factors and their highest powers, okay. That way you will calculate the LCM. I hope you are now getting a clear idea of the different ways of calculating HCF and LCM, okay, from the method of prime factors, okay. So let us proceed forward. How do you calculate the LCM of fractions? First, again, express them in their lowest terms, and you calculate the LCM of fractions by this formula. You first take the LCM of the numbers in the numerator and the HCF of the numbers in the denominator. You would get the LCM of the fractions. So let us take an example. Let us calculate the LCM of 108 by 375. 117 by 25, it's a mixed fraction. 54 by 55, that's the third number. Now first let us reduce them into the lowest terms. So 108 by 375 can be reduced to the lowest term as 36 by 125, and this mixed fraction can be reduced to the lowest term as 42 by 25. This cannot be further reduced. Now we need to calculate the, in essence, we need to calculate the LCM of 36 by 125, 42 by 50, 42 by 25 and 54 by 55. Now what are the numerators here? The numerator numbers are 36, 42 and 54. What are the denominator numbers here? 125, 25 and 55. Now what does it say? The formula says, in order to calculate the LCM of fractions, you need to take the LCM of the numbers in the numerator and divide that by the HCF of the numbers in the denominator. So let us look at the numbers in the numerator. Factors of 36, 42, 54 using the method of prime factors. You would see that the LCM of 36, 42 and 54, just write them in the, what are the distinct factors here. 2 is a distinct factor, 3 is a distinct factor, 7 is a distinct factor. What is the highest power of 2 here? Highest power of 2 is 2. What is the highest power of 3 here? Highest power of 3 is 3. And 7, the highest power is 1 only. So what is the product of this? 4 into 27 into 7. This gives us 756. Now what is the HCF of the denominators? 125, 25 and 55, you can calculate it for yourself. The HCF of the denominators is 5, the highest common factor. Okay. Now the LCM of the given fractions will be the LCM of the numerator divided by HCF of the denominator. So the numerator digits LCM is 756, the denominator digits is, HCF is 5. So this is the LCM of given fractions. Okay, hope you understood how you can calculate the HCF and LCM of fractions, of decimals, of whole numbers. Hope you are clear with that. Okay, please revise this lecture. Go back and revise this lecture if you have any questions. Okay, and please email us at easingupsc easingupsc@gmail.com if you have any further queries. So let us look at the relationship between HCF and LCM. Now, if you take the product of HCF and LCM, that should be equal to the product of the numbers given. Let us take an example. Okay, let us take this question. The LCM of two numbers is 2079 and their HCF is 27. If one of the numbers is 189, find the other. This is the formula. Please remember this formula. If you multiply the HCF with the LCM, that should yield the product of the numbers. Okay, so let us take the second number as x. Now using that formula, you can see that one of the numbers is given as 189, the other number, let us assume that as x. So when you take the product of x and 189, that should be equal to the product of the HCF and LCM. LCM here is 2079 and HCF here is 27. So when you rearrange the terms and calculate the value of x, it will yield the answer as 297. Okay, we hope the relationship between HCF and LCM from this equation is clear to you. Okay, Thank you friends for listening patiently to this lecture. We will come with solved examples in another lecture. We hope you enjoyed this initial lecture offered by us. We will come with more such lectures soon. You have a great day.